Good morning, good afternoon, good evening, privet, wherever you are, in whatever time zone you are, welcome to my talk. Today I'm going to talk about the future of data science and ML at scale and look into the Lakehouse paradigm, which is sort of the emerging data paradigm that's actually emerging. And in particular, I'll talk about how Delta Lake and MLflow fits into the grand scheme of things. But whenever you think about the future, whenever you have future in the title, you have to be careful that you're not looking into a glass ball and predicting the future. So I want to start this presentation with the good thought, with the positive thought. And this has actually been a year of good, a year of hope, a year of a lot of things, a year of data, if you call it. You know, we have seen the emergence of people now really believing in science. We've seen the value of data, and we've seen the value of statistics. And data teams across the world are actually getting together to work with some tough data problems. So we have seen this year as a remarkable year. And we have seen data teams actually come together. And data now is actually the new center of gravity. We have heard this old cliche, data as the new oil, but I like to rephrase it and say the data is really the new center of gravity. It brings people together, it brings data teams together to solve some of the problems. So having said that, what I want to do is I want to frame today's presentation in architectural level and talk about a few things. You know, what are some of the data problems that we actually face today? How is the data exploded to the point where the current architecture have some shortcomings, and we have to think about how we can actually do that and why it impedes us from doing advanced analytics at scale. And I use the term here, advanced analytics, as an umbrella term for data science, for deep learning, for machine learning, for data analysis, who actually want to deal with massive amounts of data. And then look at what are the past and the present data architectures that have evolved over the period, because in order to look at the future, you have to look at the past and you have to look at the present, and you can look and see where the shortcomings are and how things have actually evolved. Otherwise, you really can't go ahead. And how the new paradigm that has actually evolved addresses some of the challenges that today we face with the scale of the data for data scientists and machine learning to do things at scale. And then in particular, I'll try to address how the two open source platforms of open source technologies that have evolved that fit into the grand scheme of things. And just to give you an idea, that I work for a company called Databricks, and we provide this new paradigm Lakehouse platform, which is based on the idea that it has to be simple, it is open and collaborative, so the data teams across the entire organization, whether you're in data engineering, whether you're doing BI analytics, or whether you're actually doing real-time applications, or whether you're a data scientist, can work on this particular platform. And we allow you to be able to actually save all your structured, unstructured data across any of those clouds that we actually are now hosting on. And we are the original founders, original creators of very popular open source technologies, which have really, really taken off: Spark, Delta, MLflow, and Koalas, which is really pandas on steroids, and then Redash. And we've seen this huge emergence of downloads on a monthly basis of people actually adopting that. And so having said that, what I want to do is first find out what are the challenges of the data today. I mean, what are some of the problems that we face with today, and how do we actually grapple that beyond 2020? So when you look at yourself, metaphorically speaking, in the mirror, you see the sea of data. And some of the problems that actually have emerged, if you talk to the data professionals, are three things. One is the data quality. Data quality has become quite important, because if you're a machine learning engineer and if you're a data scientist, your data actually makes a huge difference on how much confidence you're going to have on your model. Staleness is another one too, because you have to make sure that the data is not stale, it's timely. And obviously the cliche, data volume and scale actually makes a matter. So if you ask questions to all the data scientists around the world, if you ask any data professional who's actually dealing and grappling with these kinds of issues today, this particular survey somehow echoes the sentiment that people expressed, where they're saying 60% of the people actually reported when Fivetran, a DBT company that actually did the data analysis surveys, that 60% reported that they have quality problem. Top of the challenge was data quality is a huge problem. And those of you who work on this particular area also will notice that 80% of the people actually reported that the data gets particularly stale over a period of 2 months. And then a number of them actually reported the fact that the 90% of the regular data is unreliable. So when they go back to the sources, they figure out that the data is actually going stale. They can't actually get back to the original data. And a similar sentiment was actually expressed by another survey that was conducted by Kaggle, where if you're a data scientist and if you are a data analyst, we all know that we spend an inordinate amount of time working on analyzing and cleaning the data, and a huge amount of time we actually do building the infrastructure, building the data pipelines that allow the downstream applications such as ML and DS to actually work on those. So those are the current crippling, enduring problems that we actually face. And the underlying question is how do we actually address this, right? How do we get the quality data that we need? How do we actually address the timeliness or the tardiness of the data that we need, which is actually a hard problem. And partly it is a problem of our own making, because we are stuck in our old ways. We are not sort of evolving with the time. The data is demanding new ways of doing things. And we are reluctant to change. We are reluctant to change because, we feel comfortable in our architecture. We've invested so much engineering in it, and we don't want to do things overnight. So that partly is that of the problem. And the second problem is partly because of the fact that data changes, and with the data, the architecture actually has to change. And if you not do that, then you're going to be left on the wayside. So in order to figure out what do we actually have to do now, and what we have to do in the future, and what are some of the vision paradigms that actually are being bandied about both in the academia and the industry, is how do we actually solve the problem? But in order to do that, we have to actually look at the history. So let's just take a peek into the past. If you go back to the 1980s, data warehouses were the cafe lattes. They were the popular sort of infrastructure where everybody almost put all their data in one single place. It was a simple platform, and it was popular for a couple of reasons. One was that it facilitated you to do your ETL from this myriad data sources that you actually get. All your operational data was actually stored in this data marts across your organization, and you could do the ETL and put it in the data warehouses, and then you actually had all this BI reports and BI analytics applications sitting on that could just directly get to the data warehouse. And the second reason was that it was purposely built for SQL and analytics, a very high performance, right? It allowed you to do analytics at scale. It allowed you to do business intelligence, to do historical analysis of what happened. And it had all the technology schemes that we actually expected from an enterprise database or enterprise warehouse, which is they had schemas to have structured table so that you know what your columns looks like. They had primary and secondary indexes to make sure that there are no constraint violations. They use the latest technology to do caching and all that. So it was actually purposely built for that particular reason. And the third was that because of the fact that there are multiple users and multiple people making changes at scale, it offered a powerful management feature such as ACID transactions. And you could actually do time travel. So you can actually go to a particular table and make sure that you actually get the right version of the table. And so that was the sort of, as I said, the cafe latte at that time. But there were a couple of issues, right? One was that, what about if the data scientists actually wanted to do something on that? It was great for data analysts who could actually just go to the tables and get that. But if you actually wanted to do machine learning, if you wanted to do data science, SQL doesn't really cut it very well. And so the data scientists had to actually extract some data and put it on the laptop and do some analysis, which was fine and dandy. But it actually worked for a number of years. But then came the 2020s, where things really took off a different turn. There were new problems for the data harvest. And one of the reasons was that data changed, data evolved. And so because of this rapid change in data, it could not support some of the rapidly growing unstructured and semi-structured data, which we actually see today on the internet or on the social media, things like time series and logs and images and documents. that are part and parcel of this particular new data. And the other thing was that there's a high cost associated with large data sets, because the data warehouses are very efficient for storing small tables, but when it comes to large tables, you actually incur the cost. And the second thing was that there was no support. And this was actually a big hindrance. There was no support for data science and ML, because you couldn't directly access data houses. You actually had to do a separate ETL to take your data out and put it somewhere else, where you can actually now can do data science and ML, because of the fact that the data is slightly different. So the question is, again, what do you do about it? How do you actually shift now in this new paradigm in the 2020s, where the data houses served a particular purpose before, but now there were some shortcomings that had to be addressed, and would you actually do that? And so obviously, we being very innovative as a human race, we came up with this new idea called data lakes. And data lakes was now the new thing in 2010s and 2020s, where all you did was you put everything, all your structured and unstructured data, you just dumped it into your data lake. And then from there, you could actually do your ETL for specific data that you actually need for data warehouses and real-time databases. So you can actually do separate ETL and put it in database. So your BI can actually do that. It allowed you to actually scale across horizontally, because of the fact that cloud storage is quite cheap, and most of the cloud vendors separated compute from storage, and therefore, as a result, you actually had the ability to scale horizontally. And so that actually helped quite a bit. And as I said, if you actually had some ETL jobs, those could actually be done separately and put into a separate data warehouse, whereby now you can actually have all these high-level workloads, such as BI and real-time and data science and machine learning. You can actually do that at scale. And then finally, you actually had machine learning libraries that we're actually familiar with, that have direct access to the data lake in Parquet or in CSV or whatever format you actually do, can now access that particular data. And there is a data preparation layer that you can actually use on top of the data lake that actually solve this particular problem. So now in the 2020s, in the 2010s, we have actually solved the problem, right? Now we can actually do both BI and data analytics at scale for the data analyst, and for the data science and machine learning, they can actually do that. So what is the problem, you actually might ask? And the problem is that today, with today's data lake, while the storage is actually cheap, the system architecture is more complex, because there are multiple processes involved. And as a result, now you actually have multiple storage systems with different SQL semantics and different dialects, in which you actually have to do your ETL. And as a result, you have multiple extra steps that can actually go wrong. So bugs do crop up when you're actually doing ETL in 2 different places or 3 different places. And when bugs up, you have to actually fix it. As a result, when you start fixing the bugs, obviously now you're introducing this new concept of timeliness and tardiness, because now the data in the ETL, the data in the data warehouse is not as recent, because you have to actually start fixing things. So as a result, timeliness suffers. And I said earlier in the survey that data quality and data tardiness was one of the problems. And this sort of introduces this concept of late data, because now you have to do data preparation for machine learning that can actually break, and that will actually require some time to fix it. And now you have data warehouses that actually have the same problem, whereby you don't have the latest data. And more importantly, and lastly, is that you actually incur high cost. And you incur high cost for 2 reasons. One is now you have the engineering costs, because now you have to continuously run the ETL and make sure that when anything breaks, you actually fix it. And then you're also incurring the cost of duplicate storage, because now you have 2 sets of data, one in data lake and partial data in data warehouses. You have to make consistency, make sure that it remains in sync. And it actually becomes quite complex in the grand scheme of things when you're dealing with massive amounts of data. And so the question now is, again, what do you do? We come at a forked road, and we ask ourselves now, we have to decide something what we have to do, because now we are running into this problem we have to figure out. And I think there is, in the 2020s now, or just in the 2021, we're beginning to hear this Lakehouse Vision that initially Databricks actually presented that in the academic conference, and you hear about this particular term being bandied about both in the industry as well as in academia. And the idea is very simple, right? The idea is, again, simple, going back to the old 1980. Have one platform, one single platform for every use case, where you have the streaming analytics, you have BI, you have machine learning and data science, who actually access data from one particular place. And what you do is your data lake now stores all the semi-structured and unstructured data as before. And what you do is, on top of that, you actually provide the management layers that is expected out of data warehouse or relational database that gives direct access and timely data to the workloads. And that is sort of the vision that has been purported and that has been advocated in the industry today, and in particular by Databricks, by saying this is sort of the new feature that we think is really going to take off for several reasons. And so the Lakehouse Systems now idea is that they actually implement all the data warehouse management features and performance features that you actually need, but they do that on top of a directly accessible data in very open formats. So when I talk about open formats, I'm talking about Parquet and Orc, which are standard open formats that you can actually very easily store and access data in a very efficient manner, because they're structured in a way so they can actually use columns to get the data. And then you build the performance layer on top of that. And once you do that, you provide programmatic and SQL interfaces to the appropriate workloads directly, and you actually provide direct APIs to the machine learning libraries that can actually access the data directly. And the management layer does all the work for you. So if you wanted to get a particular table, you just tell the management layer, on this particular table, get me this particular data, and it will know exactly what files belong to that particular table. And that's the whole idea. And so the idea is that, can you actually really pull this off, right? This is a big question. Again, we keep on asking questions when we come to a particular time where we suggest something. Is this feasible? Is that it can happen? Can we get the same state-of-the-art performance and the government features which are detected with this design? And we believe that you can actually do so. And the reason is that there is a confluence of three technologies which are actually enabling this particular Lakehouse vision. And those are, one is that there are being meta layers which are being built on top of the data lake on open formats. And these meta layers are sort of systems that allow you to do transactions, allow you to do versioning, allow you to do all the performance features that you actually expect from a high performance DW. So that's one. The second is that there are new query engines built by the industry vendors who actually have used high SQL performance engines which are built on top of the data lake based on this particular open format. And the third one is that these ML frameworks and ML libraries can have declarative access to these underlying files. So now you actually have the ability for the data scientists and data analysts to actually be able to handle data at scale. So let's look at each of these technologies that undergird, that support this particular Lakehouse vision as purported by the visionaries. So one is that Delta Lake is actually great, right? It is nice to have a huge data lake and you put all the stuff in there, and whenever you actually want something, you can actually get out of that. The problem is that Delta Lake is nothing but just data lake is nothing but a collection of files. There's no versioning in data lakes. If more than one person is updating or deleting the file, you never know which version you're actually getting it. You could actually have inconsistent data in data lakes. And so the idea is to actually provide a meta layer on top of that gives you the rich management features like transactions. So the clients now can actually access the underlying infrastructure, the underlying file at high speed. And because of the fact that Delta Lake now is actually supporting optimate concurrency, or some of this metadata layers support optimistic concurrency, you can now get the exact versions of the table with the appropriate files which are needed by the client application. So the meta layer actually takes advantage of that, and then it gives the application or the API or the query mechanism to say, if you want table 1, these are the files associated with table 1. If you want table 3, these are the files associated. If you want table version 5, these are the files associated. So all that is actually taken care of by the management layer. Now, in the open source community, or at least in the data community out there, there are sort of 3 implementations of these metadata layers that are being implemented by different vendors. One is the Delta Lake that was open sourced by Databricks and is part of the Linux Foundation. The second one is Iceberg, which was developed at Netflix and which is now part of the Apache Spark Foundation. And then Hive 3.0 introduced the whole idea about ACID. So these are the sort of the current 3 different versions of the meta layers which are built on top of the data lake that gives you the ability to do transaction, to do versioning, to do all these things that you would actually expect from a normal relational database. So let's look at Delta Lake very briefly at a high level. One of the things that Delta Lake allows you to do is that because it actually keeps track of transaction log, multiple people can actually change and delete files, and at any one point you're always going to get the exact version of the file. So either a transaction will happen or it won't happen. So for example, you can actually have one application that changing, file 1 and file 3. And when a client asks for a client that reads the version 2 of the table, it's going to give the exact files that were changed by file 1, file 2, and file 3. If they expect or ask for version 3 of the file, then they're going to get the ones which has delete on it, and you will only have the files. So that's actually maintained by the Delta Lake transaction meta layer, and that's actually done because of the fact that it actually uses transaction log, and all the transactions are created by commits in a serialized manner. And if you want to find out more about this, we actually presented a paper, and we are actually using it quite internally and by our customers, as well as advocating that this is really one of the powerful meta layers that allows us to visualize and realize and materialize of a vision. And the other management features that the Delta Lake provides is that now you can actually use both batch and streaming. So you can actually read your Delta table as a stream, and you can actually merge it with Kafka stream that's coming in to update the table, or you can actually do a batch table that you actually read and then merge those 2 tables. It allows you to do insert, upsert, delete, and merge, which is something that you would expect, say, from a relational database. And it allows you to do time travel as well. And so one of the things that, as I said earlier, was that we as data scientists and machine learning professionals want to have different kinds of data at different time in our training, so that we can actually always go back to a particular version of the table that was used to create a metric, or a version of the table that was used to train the data, or a version of the table that was used for validation, or the version of the table that had all the features that we actually need, and those could actually be stored in Data Lake. And the other thing it allows you to do is it ensures that there's a schema enforcement and allows you to evolve the schema, because data changes, and as data changes, the schema will evolve. And we want to make sure that when you put the data in, or when you insert data, it conforms with the schema. And there are options where you can say, go ahead, and the data has evolved, the schema has evolved, this is the new schema. And you can actually merge the old with the new. And then finally, the data quality is an important part. As I said earlier, we looked at the survey that where people actually complained that data quality is a huge problem. So within your code, you can actually have checks to make sure that your schema is conformant, and second, the type of the data you're expecting meets the requirements of the schema. So you can actually have expectations for the quality, and that way you can actually take care of that while you're actually updating the table as well. And so we have actually seen quite a much of adoption in the community as well, and within our customers as well, where 50% of the Databricks customers are now using Delta Lake to actually do their massive amounts of processing in terms of exabytes of data. There's a broad industry support as well. We have seen all this people, vendors on the left-hand side doing the ingestion at massive scale into Delta Lake. There are storage mechanisms that we actually store on all these cloud platforms on which Delta Lake is stored. And there are vendors who actually have written connectors so they can actually extract data from Delta Lake to make queries at scale. And so that's number one that actually is somehow, that's number one that fulfills one of the requirements. And that's why we actually see that Lakehouse is going to take off. The second is the new query engines, right? There are new query engines built that are built on top of this open format. And one of the things that we actually have done is we implemented our own SQL query engine called Delta, which actually sits on top of that. And it uses all the recent and expected technologies that you actually read to get the most efficient data. So caching your hot data after you queried the results into RAM or solid state disk, and possibly transcode that gives you the ability to actually have your hot data cached. You can actually lay out your files in different way, even though you don't have that, even though you have no control over the file format, because the file format is in Parquet, but you have the ability to how you actually lay out your data across partitions, how you actually divide the partitions, how you actually sort those particular data, how you order that, and that gives you the ability to actually add auxiliary data structures like statistics and indexes, so that way when you make a query on a particular column, you know that the range of the particular column that you're looking for is between this particular range. So you go straight into that. And that's something that's old technology that Hive actually uses called partition and pruning. And that way you only go to the columns that meet those particular statistical range. And then more importantly, because of the recent technologies, you can actually use the vectorized engines to do SMED, single instruction, multiple data. You can actually do massive parallel execution on your CPUs using the vectorized engine. And we did that using the Databricks Delta engine. And we did some preliminary benchmarks using these particular technologies, and we came up pretty good in terms of comparison using TPC-DC benchmarks across some of the competitive data warehouse in the cloud. And we weren't the best, but we were competitive in the sense that we were up there with the most leading ones. And so that is the second reason why we think that this is really going to take off, because of the fact that the Delta engine provides that, and the other engines which are being written as well. And last but least, and finally, is the optimized access for data science. And this is where data scientists now can actually use all this particular external ML frameworks that we actually have that have access and have the ability to read these Parquet files in a very highly optimized way. And if you actually use the new declarative APIs that some of the IOP further optimization gives, for example, Spark allows you to read a particular table. And if you perform a data frame query using the DSL, then that particular query is then translated into a query plan, which then can be evaluated, and the right amount of data can be pushed down to Delta Lake, pushed down predicate to the Delta Lake, so it actually gets the right amount of data and you actually get your training set. So those were sort of the three pillars of the technology. We think of three pods or three legs of the stool that actually undergird this high level Lakehouse vision that we actually are purporting. And the Lakehouse system combine both the benefits that you actually get from data warehouse and the scale of the horizontal scale of the data lakes, and simplifying the enterprise for people who actually do analytical scale. And we believe that this will really take over the industry, because we're at a time where data has exploded. Data quality is important. Data tardiness is very important. And so having these things in mind actually makes a huge difference. And we believe that simplifying the architecture and providing easy access and resolving the reliability of the freshness of data is really the next thing that we're actually thinking about. And Delta Lake actually plays a huge role in this particular thing. So I talked about the first open source tool, how it actually fits into the grand scheme of things. And the next I want to talk about is how does the MLflow fit into the grand scheme of things? You know, where does MLflow fit in, you know, for machine learning scientists to be able to actually work with this large set of libraries that data scientists use, and how it actually fits into doing the end-to-end machine learning lifecycle. So let's talk about that for a minute. Now, I'm going to begin this part of the discussion with the premise that machine learning is complex. It is difficult. And the difficulty stems not from the fact that the math behind or the concept behind is difficult. You know, obviously there is a lot of math involved in there. The concept, the difficulty stems from the fact that the methodology in how you actually do machine learning is very different from how you actually are used to doing traditional software development. The underlying infrastructure that surrounds the machine learning is more complex. And if those of you who have read Scully's paper, where you see a small little rectangle that says this is a machine learning code and this is all the infrastructure that surrounds it, speaks volumes to the fact that machine learning development cycle is complex. So let's look at why and where does the complexity emerge from, and then what we can do about it and how some aspects of it are addressed in MLflow as a platform. Now, if you look at the traditional software, and I think a good number of us hopefully come from the software engineering background and are either entering the machine learning or we are already in there, and you see that there are different ways how those are approached. In the traditional software, the goal is that you actually meet a functional specification that you're actually given, and you stick to the particular specification, you implement that. Contrast that to the machine learning goal. The optimizing is different. You have a metric, a business metric that you're actually going to solve. There's a business problem you're actually going to solve, and that is associated with some sort of metric. And the metric has some measurements associated with accuracy, or there is some probability factor. And those experiments have to be done in an iterative manner, right? You have to keep on making sure that you bring the accuracy to the point where you actually are confident to say, okay, this model now actually solves the business problems and gives us the reliable results that we expect of, given the data that we actually tried that. The second is that the quality of your product, or the quality of the end result, depends on the code and the supporting infrastructure, assuming that the supporting infrastructure is flawless, which is an anomaly, but the quality depends on the code. Whereas in the other side, the quality depends on the input data and the tuning parameters. And this is an iterative path. You have to have a lot of data actually coming in, tardy data, good data, quality data that actually comes in. And the tuning parameters is the hypothesis parameter that's you actually going to tune so that you actually get the best result, the best metric. And over time, your data changes. And so you have to worry about how you get actually going to detect that and then retrain the data. So that is a different way of doing things. Now, typically in a software stack, in the traditional software, you have maybe 3 or 4 different software stack that you actually have. You might have a few libraries you're going to support. You might have 1 or 2 languages you're going to support. You might have maybe 1 or 2 language frameworks, such as maybe TensorFlow, Keras, or PyTorch you're going to support. And the environments on which you are going to deploy is going to be very limited. It's either on premise or it's on the cloud. Nobody actually gives you CD-ROM to go and install it, but that's what your software stack looks like. Contrast that completely machine learning, it's completely different, right? The open source is completely opened up and made the developers the new kingmakers, and they want to take the best of the ML libraries available today. Because yesterday I was using NLP, now today I want to use Hummingbird, now I'm going to use Bird. All these new things which are coming up on daily basis and weekly basis in the open source, data scientists and machine learning developers want to use and compare and combine these libraries to create the best model in order to meet the goal that they actually want. And secondly, and lastly, the diverse development environments are different, right? You might have your model which is deployed on the edge. You might have a model which is deployed on your phone. You might have a model that's provided as a web service. You might have a model that's deployed on the Kubernetes. So the deployment environments are very diverse. And so you have to somehow accommodate and provide and account for and reason for all these different ways and methodologies that machine learning is different from traditional software. And if you look at your typical quintessential MLOps cycle for machine learning, that's where the complexity comes in. As I iterated, now here's a pictorial representation of it, because the process is continuous and iterative, and you have to keep on changing that. Now, in the data preparation, where you're actually preparing the data, where you're doing feature engineering, where you're doing all these kinds of things, you might be using different libraries. You might be using PySpark for ETL to get data from raw data and convert them into data features, or you might be using feature store to put data in there. You might be using pandas to do the initial exploratory. You might be using Python for that. And all of these actually have tuning parameters that you have to somehow keep track of, so that you actually prepare the data in the same way that the new data comes in. The second thing is tuning in when you're actually building the particular model. That's where the tuning parameters come a lot, because you got a hyperparameter tuning for your particular model across different libraries that you're using, and you have to keep track of those. You have to run each an experiment with different tuning parameters and compare the results of the metrics to show that you're actually meeting the goal. That's problem number one. And then obviously you have to do all this at a massive scale, right? You just can't do it with a very small set of data. You have to do that with data which is coming at you at enormous volume, and you have to somehow process that continuously. And you have to do that at a particular scale, whether you're doing it in deployment, whether you're doing it getting the raw data, and whether you're doing data preparation. Everything has to be done at the scale. And the third part is that how do you ensure that the model that you actually created, let's say Oli actually created a particular model, and she handed it to me to say, can you take this particular model and deploy it? How do I make sure that what she gave me is the model that I'm going to use to reproduce it and put it in production? So the model exchange is another part of the challenge that we have to deal with. And then finally, we are living in the data privacy, and there is inordinate amount of, especially in EU countries in Europe, about privacy. And so the governance of that particular important. How do you actually ensure that data is private? How do you ensure that the model was prepared in an ethical manner? Can I have a lineage of how the model, who worked on the model, and so on and so forth? So all these are imperatives that actually come when you're actually doing machine learning at scale. And so how do we actually address that? And how does MLflow fit into this grand scheme of things? And the way we actually approached this particular problem, and the philosophy was that, well, we really don't want to build this monolithic platform where we say use everything or use nothing. We say, let's try to do that in a modularized way. And let's try to provide APIs to the developers who can actually use that. Because if you look at APIs first principles are things that people actually build on. So we say, well, those are the 4 components that most people might need or will need. And as more components are needed, we actually start adding those things in this grand scheme of the complex cycle. So tracking is one mechanism where MLflow provides that allows you to manage your experiment, allows you to track your experiments in the tuning. So when you're tuning your model, when you're building the model, you are going over experiments, you're rerunning, retraining with each and every parameter, and you get the metric associated with that, and you want to track those so you can actually compare and contrast which was the best metric that resulted. Reproducible is an important part of it. And so if I have a particular model that somebody actually gave me, can I reproduce that model because I built that in my environment? And I might be having, let's say I use Psyche 2.1 and I use Pandas X and I use XGBoost version. I want to make sure that when I hand off that particular model to my CI/CD reviewer, he or she can reproduce that particular problem. In other words, it's in the same environment in which the model was created and developed, should be the same environment when you hand it off somewhere. So that's the whole idea about reproducing in projects. And because of the fact that we want to support all these libraries that we actually have on the right-hand side, We want to be able to actually create model flavors in these particular libraries as they evolve, so that we can package those particular model and deploy them in these diverse environments, which was a requirement for doing machine learning. And then finally, last but not least, is you need a central repository. Think of it as a Git repository where you put all the models that you actually build in an organization. It's not a public repository, but it's an organizational public repository where all the model management actually takes all the versions of the model, all the different stages the models are, the lineage of the model, who worked on the model, what stage is it, who touched this particular model, who trained, who reviewed. All that is actually handled by Model Registry. So let's go into very briefly, in the amount of time that we actually have, is the concept of tracking. Now, if you want to track something, there are a few things that we allow you to track. One is the parameters, the metrics that you actually need in order to measure your value. Tags and notes gives you the ability to document your model, so that way there's a lineage, there's a history of how the model evolved. Artifacts are files and data and models which are actually created that you can actually store alongside with that. And the source code, what code source was used, that's important. If you reproduce, you want to go back to the source. What version of the code was used, what library was used. And the run is an instance of each time when you run something, you create a particular instance. An experiment is a collection of runs. The experiment is a collection of runs. So let's look at what it actually means. So when you're actually doing MLflow in your, when you're creating or using MLflow, we have actually provided these very simple libraries that allow you to do the tracking of the algorithms. Can you guys hold on for a second? Now, and so one of the things that allows you to do that is log parameters and track parameters. And so you can actually track everything that you actually need that I showed in the previous slide and log that. And once you actually log that, we can provide you with the UI that actually gives you the ability to visualize all those in a manner so you can compare and contrast all the experiments, all the parameters, all the artifacts that are actually required. So this is sort of the tracking mechanism that gives you the ability to build your experiments, to track things that you actually need. And we believe in making things a lot easier. So we allow you to actually do MLflow tracking using autolog. So you don't have to explicitly track each and every experiment. When you say use Keras and you use the library called autolog, it's going to figure out when you do the fit or when you do the training that these are the parameters that you actually use. These are the hyperparameters actually used to create the neural network. These are all the gradients that you actually use. These are all the learning parameters you use. These are all the metrics that were generated, the loss, the accuracy, and all that. And we load that automatically for you. And so when you go to the UI, you actually see all that automatically logged to you. And your code becomes very simple, right? Your code is, here's my network and here's my Keras model, and go ahead and load things for me. So that's tracking. Now, projects is a way for you to package your data science code in a format that enables you to reproduce these particular runs. And this is actually, this can be something that you can actually develop as a GitHub repository and give it to someone and say, here's my model, and run it, and it will recreate the environment. In other words, it knows exactly what your MLflow project or what your model was built with, the code that it was built with, all the configurations, that the libraries, the versions, the dependencies are all captured, and what data was actually used to reproduce that. And once you actually have that, you can actually run it on your local environment, or you can deploy it on a Kubernetes environment, or you can deploy it on a remote machine by using this MLflow project. So that's one way to reproduce your experiment. So if I create a particular project and I wanted to hand it over to someone else to say, try this out, see you actually get the same results, because it recreates the environment. It's a unit of execution that recreates the environment. So that's a project at a very high level. The third part is models. And model is another component that allows you to be able to create flavors of the model that can be now deployed in the serving environments in Kubernetes or in Databricks or in SageMaker or in Redis, wherever you actually want to deploy this particular model, you can create a flavor of that model, and that model can now be deployed in a diverse environment. And so think of it model flavor as that these are all the APIs, these are all the frameworks that you actually support in MLflow. And what we do is we take that particular library model that you actually created, and we create an abstraction on top of that called model format. And within that model format, we create multiple flavors of it. So we can create a TensorFlow native flavor, and we also create a Python flavor wrapper around it, so you can actually deploy those models in diverse environments, in the strictly Python environment or elsewhere you actually need that. So this serves the requirements, or this serves the ability for you to build your model and then deploy in the target environment in which you want the model to be deployed. So that's model component that addresses the ability to use models and deploy them in a diverse environment. And one of the great things about model flavor is that I can actually use MLflow to train my model and to create a particular model in any of these libraries. And then I can create a Python func flavor as an additional flavor to it. And that particular Python func flavor can be loaded back into as a Python function, and then can be just used as a model to predict anything you actually want. I mean, well, I don't say anything you want, but the input signature for that will now do the prediction in Python in a Python environment if that's what you actually want. And this is actually quite powerful, because now you can actually have the ability to write these native libraries in the choice of the ML library they actually want, and then use the Python function to load them back into an environment, and then use Python APIs to do the prediction. And it underneath will actually call the native libraries to do the prediction. So this is actually quite powerful. And then finally, last but not least, the important part is Model Registry. And we all need registry where things, we have to put things in perspective. We store the models there, we annotate the models by labels, whether it's staging, production, or whether it's none or archived. It's a central repository that actually keeps track of the evolution of the model. It tracks the history of the model. It tracks the lineage of the model, how the model is actually used. So in a nutshell, when you actually are in a large organization, you might be initially one or two people might be using models, and you might use Git, or you might use version associated with the model native files. So this is version 1, this is version 2. And that doesn't scale when you have hundreds and thousands of models and hundreds of people who actually want to do that. The question is, how do you actually find out which was the best version of the model? How do you know who to actually train the model? How can you track each model history and documentation, and who actually worked on it, who reviewed the particular model? All that are important questions that people in the governance sector of the model, because now machine learning models are pervasive, they're being deployed in all industries and all verticals, and these kinds of questions are very important for auditability. How can I integrate with my CI/CD? So all these questions come into play, and that's where the Model Registry comes into play. Is that the tracking of all the results are done in the tracking server, and then you can actually store, or you can register your model with the central place, Model Registry, that actually can now have different stages, a different annotation associated with a particular model. You can have multiple versions of the same model in production. Normally, people only put one version of the product, but if they actually want to do A/B testing, then you can actually do different versions of the same model tagged as production, and then your A/B testing software can actually direct the traffic or route the traffic accordingly. Or you can archive the particular model, and then down the stream, the end people who can actually just check out the model from the registry and deploy it as a REST serving API or the REST service, or you can have automated jobs that actually take out the model and does batch inference for the data that you've gathered over the day, or downstream application can actually just embed that model in the application and actually use that. And the reviewers can go to the CI/CD tools to check the appropriate part of the model they actually need. And so, the Model Registry is actually great because it has a central place that allows you to have unique models, and each model can have different stages associated with that. along with the different versions, so that you can have multiple versions in the same stage, as I say. And it gives you the ability to keep track of the description and the history of the lineage of how the model evolved over the time. So that way you have a documentation associated with the model. And if you look at the workflow, how this actually works is quite simple. You have a developer who's going to register a particular model. Let's say we have a weather forecast model. They're actually doing a scikit-learn model. And you can actually use the log API to register the name of the model. So it's going to create a version 1 of the model. The CI/CD tool person can actually now use the client to fetch the particular weathercast model, the version 5, let's say version 5 evolved. And they did some testing on it and they were happy with the results. So they can transition the model there by using the API, or they can use the UI to do that, to the production. And then people down the stream can now actually check out the model from the registry in the particular format that actually want, and then they can actually use that. So the model registry now plays as a central part of the repository of all the models within the organization that you actually have built. And the model serving on Databricks is a new feature that we actually introduced that has the ability for you to actually take your model from the registry and then give you an ability to serve the model directly. In other words, we give you a dedicated server on which the model is served, and then you can actually use the API or the REST API to do the inferencing and generate reports and applications. And then most recently, we added this whole notion of webhooks, where now you have your CI/CD tools that can somehow be triggered based on how the model made the transitions. If the model made the transition from staging to production, you can actually associate a webhook associated with that. And when the transition happened, we trigger that particular webhook, and that webhook could be a web URL, or it could be a job that actually can be triggered, or it could be something that promotes a model or deploys that model. So all these things are all part of what I was saying, the model cycle, where we make sure that these things are part of the MLOps. And there is this blog that we have actually written, so there are links to this, and you can actually go find out exactly what this is. And just to recap, central repository that allows you to do a massive amount of model management at scale, and this is ability for you to actually discover models across the entire organization. Model Registry provides you the UI as well as the API registry to automate tasks, especially with CI/CD. Model versioning has the ability for you to actually have more than one versions in different stages, so you can do A/B testing and so on and so forth. Model stages, again, give you the ability to transition from one stage to another one. And because of the fact that CI/CD is an important part of MLOps, even though MLOps as a field, as a discipline, is still in its stages, it's evolving quite a bit. And CI/CD is an important element of it, just like it is an important element of DevOps 10, 15 years ago. It is now an integral part of MLOps. And so we provide you the APIs to be able to do that. And then finally, for provenance, model lineage is an important part of it. And so just to recap, I think we're almost running out of time. Lakehouse, again, is a new vision that we feel confident that it's going to give you the benefits of the data warehouses and the ability to scale your data and put all your structured and unstructured data in one particular format in a simplified mail that actually scales well. And this simplified architecture, along with the open source technologies that we provide as managed service on the Lakehouse platform, help you to do things at scale. And the other tools available that can actually also do things at scale, which is Koalas. And I don't have time to go into Koalas, but Koalas is, think of pandas on steroids, allows you to do EDA across the entire Spark cluster. And this is a new emerging technologies that actually is evolving quite a bit. So I think, having said that, if you want to learn more about the Delta Lake IO, these are the Git repositories and the websites. You can actually learn more about it. And if you're suffering from insomnia, I have some great links over here for you to peruse through. I really like the last two. We don't need data scientists, we need data engineers, and that's an interesting argument. I think the whole premise over there is now data teams sort of work together. It used to be the case where data scientists don't talk to data engineers and say, "These are tables I want, just do it." But now they actually work very much together because of this new explosion of data, and we have to make sure that communication is done. So that's actually an interesting article to read. And the data science is different now, again, supports the previous article where it's saying data science is different in the sense that data scientists now wear different hats because they have to think about things in scale, and they have to work with data engineers to make sure that they build and help them build the pipeline so they get the output of the input that actually the data engineers do. So I want to end this with, I started with the year of hope, that this is the year where data has actually come to the forefront of everything. We're beginning to see data taking a central role in everything. And it is also a year of innovation and adoption. We're beginning to see new technologies come on the fore to address some of the big data challenges that we actually have.